Hello guys, this is Gateville Academy and today we'll talk about stress and strain. Just pardon my handwriting, it might improve with time. Okay, so we shall talk about stress first. Stress is a sort of reaction or an internal resistance produced by the molecules within the body, under some action which tends to produce some deformation. Okay, so these are internal forces, these are not external forces, these are internal forces produced by the molecules. So these internal forces, the addition of these internal forces divided by the cross-sectional area on which these internal forces are acting is nothing but stress. Stress is denoted by a symbol sigma. So mathematically it can be written that sigma is limit delta A tending to 0 for an expression delta F by delta A, where delta F is the elemental internal force acting on elemental area. When this elemental area tends to 0, the force is sigma or stress. So now let's move on and see what are the action which produce deformation and then further produces stress in the body. So action could be force. If you apply a force to a body, it tries to produce a deformation and thus produces stresses. If there is a temperature gradient, it can also produce stress as the temperature gradient tries to elongate or shorten the object. So okay. So third, it could also be shrinkage. Okay. Now any action which tries to produce deformation within the body will cause stresses to act within the body. Okay. So now let's move on and see what kind of stresses or what types of stresses are there. How can we classify stresses? Now, types of stresses. Okay, the stresses can be classified on the nature of body on which it is acting or on the nature of stress itself. Okay, when we say nature of body, the types of stresses can be one dimensional, it can be two dimensional, or it could be three dimensional. Now let's see what is one dimensional stress. When the object has one dimension larger as compared to other two dimension, as in the case of a thin rod or a thin wire, the stresses acting along the longer direction will be nothing but one dimensional stress. Okay, now let's see what are two dimensional stresses. When the two dimensions of an object are large as compared to the other dimension, as in the case of a plate, where the thickness of plate is very small as compared to other two dimension, length and the breadth of the plate, then the stresses acting along the length and the breadth of the plate are nothing but two-dimensional stresses. The sigma x and sigma y will be sigma x, sigma y are two-dimensional stresses. Okay, so now from the one-dimensional, two-dimensional stresses, you can relate what could be three-dimensional stresses. Three-dimensional stresses are nothing but when all the sides or dimensions of an object are comparable, then the stresses acting along them are nothing but three-dimensional stress. Now let's move to the top. Here is a cube in which all the three dimensions of the body of the cube are comparable. So stresses acting along the x direction, or the y direction or the z direction are three-dimensional stresses. The example of three-dimensional stress could be an object immersed in water. Okay, the object immersed in water is an example of three-dimensional stress. Okay, so this was a classification based on the nature of body. Okay, then there is a classification on the nature of stress. Okay, so let's move on to the classification on the basis of nature of stress. Okay, so if there is a body, let's take a cube again. Let's take a cube again, and if we see, the internal reaction that is produced under some action might not be fully perpendicular or might not be fully parallel to the surface. It might be at some angle. Okay, let this be F. Okay, so if this is X direction and this is Y direction and this is Z direction, okay, so on this plane A, B, C, D, the internal reaction that is produced is F. Okay, so it will have a component F Y in Y direction, Fx in X direction, and Fz in Z direction. These three components of the internal force F will produce three internal stresses: sigma X, sigma Y, sigma Z, acting upon the area ABCD. Okay, so these stresses sigma X and sigma Z are parallel to the surface ABCD, and sigma Y is normal to the surface ABCD. So this sigma Y is called direct stress, and sigma Z and sigma X, which are parallel to the surface, are called shear stress. Okay, so direct stress tries to elongate or compress the body, whereas shear stress tries to distort the body. Okay, so now let's see strain. So now we shall see strain. While stress is an abstract quantity and cannot be seen, strain is different from that. Strain is a concrete quantity. It can be seen, it can be felt, and is measured directly as a relative change of length and shape. Okay. Now strain can be classified in same way as stress. From direct stresses, it can have direct strain, it can have direct tensile strain, it can be direct compressive strain, then from shear stresses it can have shear strain. Okay, so now let's see what is direct tensile strain. Stress was represented by sigma, whereas strain is represented by epsilon. Now tensile strain is represented by epsilon with a subscript T for tensile stress. Okay, so this is equal to increase in length divided by the original length, whereas the compressive strain epsilon C, subscript C for the compressive strain, will be reduction in length reduction in length divided by the original length. Okay, so these are very basic definitions. Now let's move on to shear strain. Shear strain. Let's consider a two-dimensional object A, B, C, D. Okay, now there is a shear strain acting along the CD dimension of this object, which will try to distort this object. So the new position, let it be C dash, D dash, and the distortion produced, let it be gamma. Okay, this is the change in the dimension CD to CD dash. Let this be ds, and the length of the object, let it be L. Okay, so shear strain is nothing but ds by L. This is the distortion produced. So this will be equal to tan of gamma. In civil engineering, we see a very less distortion, not a very huge distortion. If this distortion is less, this tan gamma can be represented by just gamma. Okay, now let's move on to stresses produced by the strains produced by 3D stresses. These are volumetric strain and are represented by epsilon with a subscript V. This will be equal to change in volume divided by original volume. Okay, by original volume. Okay, so now let's move on to something else also. If there is a cube, okay, which is acted upon by 3D stresses, now there will be some stress sigma xx, there will be some stress sigma yy, and there will be some stress sigma zz. Corresponding to these, there will be strains epsilon xx along the xx direction, there will be epsilon yy along the y direction, and there will be epsilon zz along the z direction. So the volumetric strain epsilon v will be equal to epsilon xx plus epsilon yy plus epsilon zz. This has been derived in many textbooks, and we will derive this in the next lecture. So the volumetric strain is the sum of all the direct strains in all the direction, along the x direction, along the y direction, and along the z direction. So we'll meet in the next class. Till then, bye.